This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion centers on a research paper exploring stable neural stochastic differential equations, SDEs, for analyzing irregular time series data. The authors propose three novel classes of neural SDEs to address challenges posed by real-world data. What are the primary limitations of conventional methods when dealing with irregular time series data?
Traditional methods like RNNs, LSTMs, and GRUs treat time series as discrete sequences. This approach struggles with irregularly sampled data or missing values, common in real-world applications. They fail to capture the underlying continuous time dynamics inherent in many time series processes.
The paper introduces neural ODEs as an alternative. How do neural ODEs improve upon these limitations, and what are their own shortcomings?
Neural ODEs use neural networks and ODE solvers to learn continuous latent representations. They model continuous time dynamics, but they are deterministic and don't inherently handle stochasticity or uncertainty present in many real-world time series. Furthermore, they struggle with incorporating incoming information effectively.
Neural SDEs extend neural ODEs by incorporating stochasticity. Why is this extension non-trivial, especially with irregular data?
The addition of a diffusion term in neural SDEs is not straightforward. The behavior of the solution to an SDE is highly sensitive to the choice of drift and diffusion functions. Poor choices can lead to issues like the absence of strong solutions, stochastic destabilization, or unstable Euler discretizations, severely impacting performance.
The authors address this by proposing three stable classes of neural SDEs. Can you elaborate on these classes and their key characteristics?
They propose neural Langevin type SDEs, LSDEs, neural linear noise SDEs, LNSDES, and neural geometric SDEs, GSDEs. Each class uses theoretically well-defined SDEs, ensuring stability. LSDEs are motivated by Langevin SDEs and have a unique invariant measure. LNSDES use linear multiplicative noise. GSDs have properties similar to deep ReLU networks, such as a unique positive solution and an absorbing state at zero.
The paper emphasizes the robustness of these proposed neural SDEs under distribution shift. How do the authors demonstrate this robustness theoretically?
The authors leverage stochastic stability analysis. They derive non-asymptotic upper bounds on the difference between output distributions for original and perturbed input data, for example, due to missing data. These bounds show that the proposed neural SDEs are less sensitive to input perturbations, preventing overfitting and maintaining performance under distribution shifts. The size of the perturbation and the depth of the neural SDE influence the bound.
The authors also incorporate controlled paths into their neural SDEs. What is the purpose of this addition, and how does it improve performance?
Controlled paths, like cubic splines, are used to represent the irregular time series data. Incorporating them non-linearly into the drift term allows the neural SDEs to effectively capture sequential observations and improve their ability to model the temporal dynamics of the data.
The paper presents extensive experimental results. What datasets were used and what tasks were performed?
They used 4 benchmark datasets: PhysioNet mortality, PhysioNet sepsis, speech commands, and MuJoCo. They performed interpolation, forecasting, and classification tasks. They also conducted a robustness analysis on 30 public datasets with varying missing rates.
What were the key findings of the experimental evaluation?
The proposed neural SDEs consistently outperformed state-of-the-art methods across all tasks and datasets. They showed superior performance in interpolation and classification and maintained high accuracy even with significant missing data rates. The ablation studies confirmed the benefits of using controlled paths and nonlinear diffusion functions.
The paper mentions that the proposed methods are less memory efficient than some alternatives. What are the trade-offs involved in choosing these methods?
The improved stability and robustness of the proposed methods come at the cost of increased computational resources and memory usage. The choice depends on the specific application and the prioritization of accuracy and robustness versus computational efficiency.
The theoretical analysis relies on certain assumptions about the neural networks used. How realistic are these assumptions in practice?
The assumptions, such as Lipschitz continuity and linear growth conditions, are common in the neural OD-SDE literature and are generally satisfied by neural networks with common activation functions like TON, ReLU, and sigmoid. However, the specific values of the Lipschitz constants and growth rates can impact the tightness of the theoretical bounds.
The paper highlights the importance of careful design of the drift and diffusion functions in neural SDEs. What are some practical considerations for choosing these functions in real-world applications?
The choice of drift and diffusion functions significantly impacts the stability and performance of neural SDs. The author's proposed classes provide a starting point, but careful consideration of the specific characteristics of the data and the desired properties of the model is crucial. Experimentation and validation are essential to determine the optimal choices for a given application.
The results show that the proposed methods converge more rapidly and achieve lower loss values than naive neural SDEs. Can you elaborate on the reasons behind this improved convergence?
The improved convergence is likely due to the theoretically well-defined SDEs used in the proposed methods. The careful design of the drift and diffusion functions ensures stability and prevents the numerical instability issues observed in naive neural SDEs. This leads to more stable training and faster conversions.
What are some potential future research directions stemming from this work?
Future work could focus on improving the computational efficiency of the proposed methods, exploring different types of stochastic processes beyond Brownian motion, and investigating the applicability of these methods to other types of time series data and tasks. Further theoretical analysis could also explore the impact of different hyperparameters and network architectures on the stability and performance of the models. Applications to specific real-world problems, such as financial modeling or healthcare, would also be valuable.
This has been a very insightful discussion. Thank you for explaining the key aspects of this research.